will talk today about agricultural robotics and the problem of dealing with variation and occlusions. And basically, I would like to argue to you and hopefully probably during this talk that robots should become aware of what they cannot do, what they don't know, and they should also be aware of what they cannot see. So, first of all, a little bit for people that don't come from an agricultural background, a little bit of an introduction of why we use robots in agriculture in the first place. Well, we have the globe. We have big challenges. So the first challenge is, and we saw also yesterday in the talk in one of the keynote talks, that we have a growing world population. It's growing up to 9 million people in 2050. People, of course, need more food. That's clear, but they also need more feed for the animals. We need more fibers for our clothes, etc. So this puts a large strain on agriculture. We just need to produce a lot more. In the next 30 years, we need to produce 70% more. That's at least what's predicted. But on the other hand, there's a problem with scarcity. The scarcity of water in many regions in the world due to climate changes. We have problems with fossil fuel. That's very clear at the moment, right? But also we have scarcity of human labor. It's a little bit contradictory because we get more and more people, but fewer people are willing to work in agriculture. And that's because most of these tasks are pretty hard. You have to do the same thing in tough conditions, very repetitive and dull work, so people are not willing to work in these environments. And last but not least, the impact of agriculture on the environment is enormous. Greenhouse gases, waste, chemicals, diseases. So in short, we need to produce more, but we need to do it with less. That's the challenge that we have. And this is a big challenge, and robotics is definitely not the only solution. But robotics can be one solution. So this, for instance, in one of the pictures that we have in Wageningen, vision that we have, we should go for a more inclusive agriculture where we grow different crops in the same place, and so that we don't need to have a lot of chemical, because there's a good biodiversity, it's insects that kind of help each other out, plants that help each other out. So this is a much more sustainable way of farming. But the problem with this type of farming is that currently we cannot do it because it's very labor intensive. Right, so why is agriculture so productive at the moment? Well, we have monocultural fields, big fields with the same crop on there. We can have big machines that harvest, the harvesting operations and the seeding operations. If you want to go to this vision of agriculture, this cannot be done. We need robots to do the work. Now, if we can have robots, we can do this precision agriculture. We can treat every plant exactly the way that it needs to be treated. And that helps us to go to this more ecological way of farming. And we can improve the resource efficiency. We know what the plant needs. We can minimize the use of chemicals, minimize the use of water, and just apply it only there where it's really needed. That reduces pollution and waste. Also, robotic systems, computer vision systems can be used to help improve breeding. If we know better how plants are behaving, we can breed faster for better, more robust varieties. And clearly, we can also solve this labor task. With this reduced cost, and in the end, the reduced cost is for a farmer a big incentive to go for robotics. However, we don't see robotic systems much in agriculture. There are a few examples, but mainly there's a lot of promises. We have robots that can do things, but they are typically not robust enough so the business case doesn't hold for the farmer. And why is this? Well, I think there are at least two very important factors. And the first one is variation. And this is just a sample of a few tomatoes. You can see that there's a huge variety just in the set of tomatoes. That's variety within one cultivar, within one species of tomato, but there are also many different species. And then there's incomplete information. You go into a greenhouse, you see pictures like this, where a lot of the information that you need is actually hidden. Right? So I'd like to argue that we need more robust perception systems. We can vary with the variation. And we need active perception. Robots that actively look around, gather information so that they get what they actually need. So that's what I want to talk to you about today. So let's start with the challenge of variation. Well, there are different types of variation. I already showed you the differences in appearances, but if you go into a greenhouse or you go into an agricultural field, there's a huge influence of the environment. Sunlight, moisture, that creates difficulties for the perception system, but also for the operation. There are differences in cultivation systems. In the Netherlands, we grow the tomatoes like this. But in other places in the world, you go tomatoes in a different way, and the plant moves different because the maintenance is done in a different way. And also, we'd like to go for robots that can solve multiple tasks. It was only one thing, not only a harvesting robot, but also a robot that can maybe de-leaf or rehang the plants, so that they're more economical. Well, we're going to talk today about the variation in objects and the environment. So here's a study that we did a few years ago where we took data from 22 different fields, and these are fields with sugarbeet plants on it. You can see the sugarbeet plants. And in these fields, the previous year there were potatoes growing, and well, for reasons that I can tell you later in the breaks, but these potato plants really need to be removed because of the soil quality, the problems with nematodes. So we'd like to detect this is away from the potato plants are in the sugarbeet. We actually like to detect both. Right, but this is 22 different fields with different cultivars, so different species, different soil types, also different growth stages. So that creates a lot of variation. And then we just took an off-the-shelf object detection method. You will be three here, but the results will apply to any other machine vision algorithm as well. And what we did here is that we took 200 images in the training set. No, sorry, 500 images in the training set. In every case, 500 images, but we changed the amount of variation in the data set by picking either the 500 images for only five data sets, or to pick it from 20 data sets. But in any case, always 500. But what you can see, if we sample images from more training sets, the improvement is very visible, right? So we don't necessarily need more images, and we need to make sure that we have enough variation in our data set. Then, of course, you can also gather more images. So that's what we did here, starting with 250 images in the training set, going up to 8,000, and also there it's clear that you improve your performance of the detections. Right? So variation is important in the data set, but also the quantity that we need. Right? And then we can put that into the reality, right? Train the system, run it on a field, and then with the system we can do a precision spraying, small spots, a few centimeters. We can precisely target only the potato plants so that we remove those and the sugarbeet stays there. And this gives a great reduction of the use of chemicals. So what happens? In the end, we have a distribution, let's say in green of the sugarbeet plants and in red of the potato plants. And in order to have a system that really works for every farmer in every field, in every condition, we need to cover that whole area. But in our data sets, maybe we have covered with the circles. So we can deal with some situations, but we can not deal with many situations. On the one hand, we can gather more samples from our fields before we get this situation. So you get a little bit more variation perhaps, but still you don't cover the whole area. On the other hand, we can sample for more variation. You might get something like this. We get a better coverage of the whole distribution, but still the spots are too small. And if you combine them, you hope that you get enough data to sample this whole field. But now this brings us to the question: how do you sample in an efficient way so that you get this, so that you get a good coverage of your distribution in the test set? And that brings us to the topic of active learning. So it is just simply the case that agricultural robotics for a long time will see new situations that have not been covered in the training set. Right? And we need systems to become aware of this. Instead of just applying the algorithms and going with false detections, we would like to have the system being aware of the fact that he doesn't know, he or she doesn't know. Right? And because if you do that, then, well, the system can get help from a human being to retrain the system. Now, this is a different study where we detect broccoli heads. This is for automatic harvesting of broccolis. And on the left, you can see a healthy broccoli. This is the broccolis that we would like to harvest. And there can be all kinds of defects. It can be that the broccoli heads are damaged, or they can be over-matured. That's the C, and B, catch eye is a specific disease, or the head rot. So we need to be able to classify that. What we did to make the system aware of what it can and cannot do, we used master CNN algorithm, which is standard off the shelf. But then we added Monte-Carlo dropout in the box head and in the mask head. The Monte-Carlo dropout at random disables parts of the network, so that and then we do this not during training, or we also do it during training, but everyone's doing this to make the system robust, but we do this during inference. Right, so we run this network, disable part of the layers, part of the connections, and then we get a prediction. Then we do this multiple times, and every time there's a random dropout of these connections. So you get slightly different answers from the system. And the idea is that if this is very consistent, the predictions are consistent, probably the system is very certain. But if it's inconsistent, it's uncertain. This is gives the uncertainty of the model, so we call epistemic uncertainty. And this is an example here, a little bit difficult to see here, but you see that the segments on the three different runs look very similar. So the network is pretty sure about where there's a broccoli head. The classes are different. In all three cases, the color indicates a different class. And it predicts a different class. And of course, we need to know if it's a healthy broccoli head, yes or no. And so we take this, we can calculate a certainty values. You see that the certainty value for the spatial location, so for the box and for the masks, is very high. So we're pretty certain about that. But for the semantic certainty, the certainty about the classification, it has a low value. Right? And then if we do that, we can go for an active learning approach. So we have an initial training set, some data that we gathered, and we took that to train our model. And then we can run the model either during operations, or in this study, we gathered a large set of unlabeled images, right? And we can run this network on the unlabeled images. And it's predicting its output, but we're not interested in the output, we're interested in its certainty prediction, right? Because we can then sample the, say, 100 or 200 most images that the model is most uncertain about. We take those, we label them, and then we add them to the training set. Right? And doing so, we can train the model again, run it on the unlabeled images, and continue that operation. Right? So we have this model now selecting its own data, the data that probably, we hope at least, is most relevant for the system to learn, right? To fill up the space of the distributions of the problem. And that's also what we see. So in blue, you can see here the line for random sampling. So if you just randomly select images, it's also in blue. Makes sense. And more images, I already showed you before, gives us a better performance. But if we use this active learning, we increase much quicker. So with fewer samples, we get already to a higher level of performance. And with the black line, we indicate what we can get if we use 14,000. So that's all the images in the unlabeled pool. If we use 14,000 images, that's the level that we get. And after 2,500 images, we're not there yet, but we're approaching. Okay, so brings us to this idea of getting a grip of uncertainty. I'll bring you to a different application. In this case, it's about the detection of chicken and the plumage condition. So it's a chicken, if they're healthy, they have a good set of feathers, that's called a good plumage condition, but they might be pecking on each other and there might be issues with the feather condition. And we would like to see this in an early stage. We put cameras in the farm to continuously monitor the animals to be able to detect that. However, it can happen that the quality of the images is not good. You can have these motion blur every now and then. It could be occlusions, one chicken occluding the other chicken. Still, the network in the previous version was predicting its plumage conditions, but it was often false or error. Now we look here at the epistemic uncertainty. That's actually the same as what we did in the previous study. But we also look at the aleatoric uncertainty. That's the uncertainty that you get, not because the model doesn't know, but because the data is not good, like in this situation. Right? Now, what we did here to get this model uncertainty, again, we used Monte-Carlo dropout, similar to what we did before. To get the aleatoric uncertainty, we actually have the network predicting, or at least to predict, that in this case is plumage condition, but it also predicts the uncertainty on that, which is captured in the variance, sigma squared. And the nice thing is that there are loss functions that you can use to train this implicitly. So we don't have to give it a ground truth uncertainty, because that's something we don't know, right? But we can learn it through this loss function. And we implicitly learn both to predict the value, but also to predict the uncertainty that we have in that value. Now, and then if we look at that, this is the aleatoric uncertainty for original cases where we see the chicken well, this is just a good quality image. If the head is occluded, still the uncertainty is low. And that makes sense because the head is usually not important for the feather condition. But then if the center or the back of the animal is covered, is occluded, you see that the uncertainty is much higher. So the model seems to understand that for these cases, it cannot make a good prediction. And also for blurry images. Now here's a plot where we have the error. So that's the true error in prediction. So compared with the ground truth labels. On the x-axis and on the y-axis, we have this uncertainty value. Don't bother about the gray points, by the way. But in blue, we have the epistemic uncertainty, and in orange, we have the aleatoric uncertainty. And you can see that both are very much correlated with the error. And that's a very good thing, because this shows that the method is aware of when it will likely make an error. It's not perfect. You see the dots going around. It sometimes is still certain about the wrong prediction. In many cases, it's actually, it knows. But then if that's true, then we can also filter out our predictions. So here on the x-axis, you see the number of rejected images. But 0%, we just have the nominal performance without doing anything with the uncertainties. But we can then reject images that are uncertain, or where the model thinks it is uncertain. And what you see, again, ignore the gray line, that the aleatoric uncertainty and for the epistemic uncertainty, the performance increases. So the accuracy of the predictions increases when we take into account this uncertainty. So that's a good thing. So I would like to state here, agricultural models need to become aware of what they don't know, so that we can help them to improve. How am I doing the time? Yeah. How much I have left? 8. Okay. Yeah. Okay, so then move on to the next challenge, and it's the challenge of occlusions. Well, first of all, are occlusions a problem? Well, yes, they are. And this is a case of, again, a different application. It's about the counting and classification of fish. This is data captured on board of a vessel. After the catch, fish are put onto the conveyor belt. We take images of that. We track them over the line. So we can then get countings of how many fish there are for certain species. Now, if you then look at how well we're doing compared to the level of occlusion of fish, this is what you see. So if a fish is heavily occluded, that means a large part is covered by another fish or stones or mud or whatever, then we have a drastic decrease in the performance of the system. So occlusion is really a big problem in this type of system. Now, there are different ways to deal with this. One thing that we tried is to actually have models or train models to predict what they cannot see. But here again, this is broccoli, and that's a very small part of the broccoli visible. And most part of it is occluded. Well, can we train a model to predict what it cannot see? And so, in order to do that, we took this network, which is a modification of mask RCNN. So it's predicting the visible mask in blue. That's what all the models do. But it also predicts an amodal mask. An amodal mask is actually the mask as if it was not occluded. And if you subtract the two, you can get an occlusion mask. Now we trained that system taking images in the field. So on the left, you see an image of the natural situation. That's the broccoli head covered by leaves. And on the right side, we remove leaves in order to have the whole broccoli head visible. So then we can use the right side as the ground truth for the left side image. And we trained that on a set of images and tested that and validated and tested that. And we use that then to estimate the size of these broccolis. So for the automatic harvesting, it's important to get the size right. If they're too small, you want to leave them on the field. If they're too big, well, they need to be taken off the field, but they cannot be put into the supermarket because they are worth less. So you want to know the size. So what we did is we used this occlusion RCNN to get this amodal mask. And from the amodal mask, we then trained another smaller network to predict the size of these broccolis. And for the mask RCNN, we tried to do something similar, but of course we don't have the full area. So here we used the standard method to fit a circle on the mask that we can see, and use that to predict the size of the diameter of the broccoli head. And if we do that, then you can see here in blue what happens with the occlusion RCNN. So if the occlusion rate is low, that's on the x-axis, both methods they perform equally well. But if you get to more occluded situations, which do happen in the field, right, 60%, 70% of occlusion, and predicting what we cannot see helps us a lot to estimate this data. But another way to deal with occlusion is to use multiple viewpoints. In this case, again, a different application. This is about the pose estimation of animals. Right? From the pose, over time, we can predict the gait of an animal, and this is a sign for the well-being of the animal. Again, we install cameras that continuously monitor the cattle, and so that the farmer can be warned if there's something wrong. But what often happens is that there are occlusions. There are fences, poles, trees, whatever. And in this case, we artificially added occlusions. And if you have these occlusions, you obviously have difficulties to detect the key points, the joints of the animal. But if we take a standard lead network, so this is one of the networks for pose detection, and we extend that by not only taking the single image, but taking a sequence of images, and we can build this temporal lead model, where we now have instead of 2D convolutions, we use 3D convolutions all over the network, so that the information, the temporal information, can also be taken into account. Right, and then we can see that we can deal with this much better. Here on the left, you see a prediction of the occluded images when we only use one image, and then there are a lot of errors in the joint positions. But if we use already two images in sequence, we're doing a lot better. So what you can see in the graph are the orange bars. Interestingly, in this case, if we use a sequence of 4, the performance decreases again. And that turns out to be the issue related to the size of the occlusion. These occlusions are rather small compared to the motion of the animal. So with 2, we already gather enough information, which means we use 4, or we need to train that model because we have many more weights in the model. We need to train that model with much more data. We didn't have enough data here. But if you increase the size of the occlusions, it becomes more important to have a longer sequence. And this allows us to do so. So that's also a way to deal with occlusions. So the last thing I'd like to end this talk with is to motivate you to think about systems that deliberately deal with occlusions, right? Because taking a sequence, you're still down to luck if in the next image you see what you really need to see. But robots can reason about what they can see and what they cannot see to make viewpoint predictions that give us as much information as possible. And this is an illustration of that. In this case, we want to reconstruct a plant, a tomato plant in this case. And we have a current reconstruction. Let's say we have 40% of the plant reconstructed. And now we can sample new viewpoints. What if we go upwards? Can we maybe predict how much information gain we expect there? And if we go downwards, what will happen? And then we can choose the sample, the viewpoint that gives us most information. So this is next best view planning. And in this case, we use occupancy maps where we have a sense of occupied space and unoccupied space, but also uncertainty on that. And for the locations in space where we have high uncertainty, if it's occupied or not, we can gain a lot of information, or at least we predict that we can gain a lot. We can then sample viewpoints that give us information. And on top of that, we added a system that is task specific. So if we need to monitor the whole tomato plant, which is maybe necessary to predict the yield or to give information to a grower or to a breeder, we need to scan the whole plant. But maybe if we want to only do harvesting operations or we want to take leaves out of the plant, we're only interested in the leaf and the fruit nodes. Or maybe we want to zoom in even more. Right? And we can do that by putting an attention mechanism on top of it, to regions of interest to scan this. But in this case, we did this study in simulation because it's really difficult to do in reality. It takes a lot of time, and there's no ground truth of the reconstruction of the plant in reality. We did this with 20 plants in different random positions on many runs on this same system. And we allow the system to plan in the semi-cylinder. And we do that for the models that take into account this sense of information gain. We also do it for a random planner. And to be honest, this already helps the random planner a lot, because in this case, we always focus to the center of the plant. So any viewpoint randomly selected is actually already informative. Whereas if you completely have this in all the degrees of freedom free, and of course, random planner will start looking up to the ceiling and not getting any information. But by doing so, on the left you see what we get if the task is to reconstruct the whole plant. You can see different lines make a little bit difficult. You can see that in orange you see the random line, and that's running much lower than if we have this model that takes into account the region of interest of the whole plant and plants new viewpoints based on information. And we get a faster increase in the reconstruction of the plant. And if we're interested only in the nodes, this difference is even more apparent. We then focus the information on the stem of the plant, or where we expect the stem to be happening. We get that information much quicker. And the next step, of course, to do is iteratively. Currently, we set the region of interest on the stem by hand, roughly. Of course, we need the robotic system to automatically set these regions of interest. But that's something we're working on right now. And that's something we can do. So you take parts of the stem, you can then estimate the size of the region of interest, and this can dynamically change. And it helps us a lot to get the information that we need. This is play. Just to end off, this is one of the runs. We can see what's happening. So, robot reasons about space. On the right, you see the occupancy map. This is the part of space that is certain about the occupancy. What you don't see is that it also has information about the parts of the space that has not been explored. That's what it's using. In blue, you can see all the candidate viewpoints. For every viewpoint, we analyze the information gained, and we take the viewpoint that gives most of the viewpoint. So, the other thing I would like to give you as a take-home message is that agricultural robotics need to become aware of what they cannot see. Right. So to wrap up, I showed you that there's a problem in agricultural robotics to deal with variation and occlusions. This is one reason that these robots in practice are not a commercial success yet. On the one hand, there are often new situations that these robots encounter, and they need to be able to deal with this. But they need to know if they don't know. They cannot deal with this. So that we can use active learning to improve the system as efficiently as possible. On the other hand, we need to deal with occlusions. We can use deep neural networks to predict occlusions. We can use multi-view perception to better deal with occlusion. But what's even more important is that robots need to become aware of what they cannot see so that they can plan viewpoints to deal with the occlusion. With that, I'd like to thank you for your attention and open for questions.